Okay. Now I'm being heard. Is that true?
Yes.
Okay,
Yes.
good, good, good. There's a new button on Zoom these days. It's a security button because of Zoom bombers. So these are people who drop into your meeting without any notice and do things that most people would rather not have happen during a meeting. So I should be able to react quickly to that. Zoom has become a very popular place to be a mischief maker. The other thing, so I keep getting asked by the provost to do stuff, but some of it not so much fun. But the latest one is they want to provide to the people of Pima County the best information, at least on the progress of COVID-19 in Pima County. So I talked to a public health nurse at the Department of Health, and she's going to give me some epidemiologists today, and then I'm going to put them in contact with some sort of data scientists and statisticians, and we'll try to put up a web page to keep people informed on COVID-19 locally. So if you have any information or any suggestions on how you would like it to look, then send me an email, and we'll take advantage of it. This seems to be a high priority for the university to try to keep people informed. And it's a good aspect of a Research One university that it takes informing the people who live around us what's going on in critical issues. So are there any, before I go into the lecture, are there any questions about the homework? Of course, I have an office hour at 2 o'clock today where we'll go on that in much more detail, but if there's anything quickly right now that you would like to ask, then that might, I can go through that. So we'll look at the second one, interval estimation. These are going to be more sophisticated techniques or different strategies to try to build an interval. They mostly focus around the idea of pivots. And so we're going to look at pivots for special families of random variables. And then we're going to look at a pivot more abstractly that uses the probability transform. So what makes things a pivot or a pivotal quantity? The letter that typically uses Q of X and theta, so it's a random variable. So there's a capital X in there. And it's called a pivot. And it's sort of stating the obvious, but it's a function of X and theta, but that means there's nothing else hanging around back there that we're not talking about. In particular, there's nothing unknown inside of Q except the parameter theta. And if you look at the distribution of Q of X and theta, doesn't depend upon theta. So if I have a piece of theta and then I have an object inside the braces that asks a question about the random variable Q, then the answer, that probability, will not depend upon the parameter value theta. So typically P sub theta of Q of X and theta landing in some set will have a probability, and that probability will be independent of the value theta. And that makes it a useful argument or a useful tool or useful random variable for creating confidence intervals. So if we start off with independent and identically distributed random variables, if they come from a location family, what does that mean? That means that the densities can be indexed by a single density F, and then the others are gotten by translating left and right by an amount theta. So then if I let Q of X and theta be any linear combination of xi minus theta, then that doesn't depend upon the value theta, right? If once I knew the true value, then I just translate it back and forth to take care of that. So that's a pivotal quantity. In particular, if I replace all the a sub i's by 1 over n, then that Q of X and theta becomes X bar minus theta. And that's a pivot for a location family. And you can see that we might use that as confidence intervals for the mean. If the X sub i's arise from a scale family, what does that mean? Well, in the case of a continuous random variable, you have this product or this factor of 1 over beta in front of the density. And that comes from the chain rule or the change of variable formula. For densities, if it's from a discrete random variable, the 1 over beta won't appear, but I'm going to stick today to all continuous random variables. Then if I take any linear combination of the xi's and divide it by beta, that's a pivotal quantity. And the one that I'm going to spend the most time looking at is just the sum. So if I look at the sum of the xi's, it should be xi is a pivot. If the xi's arise from a location scale family, then you have to put several things together. I won't mention all possible ways to get pivots from a location scale family, but the one I will mention is this standardization, right? That is x bar minus theta over s, where s is the sample standard deviation, is a pivotal quantity, right? It doesn't depend upon theta or beta. The subtraction of theta takes away the dependence on theta, and then I have a quantity in the numerator, x bar minus theta, that depends linearly on theta, and I have a quantity in the denominator, the standard deviation, that depends also linearly on theta. And since I'm looking at the ratio, the dependence upon, on beta disappears. So that could be a pivot, and that's the pivot you might expect that we've used for the t statistic. So we talked about ancillary statistics as a statistic that does not depend upon theta. So just to either relieve confusion or sow confusion, I want to tell you that it's not an ancillary statistic. In fact, it's not even a statistic, right? Because you're not allowed to cheat when you talk about statistics. You're not allowed to contain any unknown parameter, but we explicitly in these pivotal quantities put in this unknown parameter that we can use for the pivot. Okay, so now I'll start building confidence intervals. So for a gamma level confidence interval, I want to find an upper limit and a lower limit, a lower limit, which I'm going to call L, and an upper limit, which I'm going to call U, well, so that the quantity that the pivotal quantity Q of X and theta, that should be a capital X and theta, lands between L and U as some value gamma. And since it's just an event that uses a pivotal quantity, then by definition of pivotal quantity, that probability is independent of theta. And then I'll define the confidence interval to be those x's for which those data for which the pivot lands between the lower limit and the upper limit. So let's do some. And then just almost by definition, the probability that theta lands in that confidence interval is gamma. So that's how that's one of the ways we're going to do it. So if the Q of X's we have are monotone increasing in theta, that's a typical example, then the situation at the top of the line looks a little easier. So if it's monotone increasing, then I'll fix X, fix your data, and then I have a formula in theta, Q of X and theta. Okay, I want to solve that when that is equal to some quantity L, and I'll call that theta hat L. And not surprisingly, I'm going to do the same thing at the upper end. So I have Q of X and theta equals to U, and since it's monotone increasing, there's an inverse, and that inverse function has a solution equal to U. The inverse of U is that. To get the inverse of that function, then I have to plug in the value theta hat of U to get the value U. So the confidence interval is exactly the same. The line at the top, L less than or equal to Q of X and theta less than or equal to U, is exactly the same as theta L of X being less than or equal to theta being less than or equal to U. I just use the inverse function and the fact that if Q is monotonically increasing in theta, then the inverse function is monotonically increasing as well, and so I can use that to keep the order of these three quantities L, Q, and U for the confidence interval written in terms of the pivotal quantity, and theta hat theta and theta hat sub L, theta and theta hat sub U in the confidence interval. So typically we'll do that inverting. For Q of X monotone increasing in theta, then just reverse the rules of theta L and theta U. Everything looks the same, you just have to appropriately deal with the inequalities. Okay, so if X comes from a location family, and the density is as we've seen before, is given by one given universal density F, and then X minus theta. So the normal distribution is an example of a location family. Then we can take X bar minus theta as the pivot, and then we want to choose gamma, so that this is again the definition of a confidence interval using the pivot, so that Q of X and theta lies between L at the lower limit and U the upper limit. And so if my pivot is X bar minus theta, then I'll just substitute that into this string of inequalities replacing Q, and then I'm just going to isolate theta, right? Because I want to know something about theta. So it's easy to isolate theta. In this case, I'll subtract X bar from across those three equations, keeping the order, and that gives me L minus X bar is less than negative theta is less than U minus X bar. Then I'll multiply through by -1, and that will reverse the orders of the inequalities. So it's now X bar minus L is greater than or equal to theta is greater than or equal to X bar minus U. And so now I have to just put in what those values are to give me the confidence level that I care about, give me the probability gamma. So for example, if my data come from a location family from the normal random variables, in this case, the variance is fixed. So that means that if I translate my data or my observations by a value theta, then it stays in that family. Then I can take L to be the negative sigma naught over the square root of n times this critical value, which is the upper tail probability, where I put half of the probability below that value, and then U is the same quantity with a plus sign, so I put it above that value. So pay attention to plus and minus signs here, right? So I have X bar minus L, and L is minus something, so that means that's the bigger of the quantities, and then I have X bar minus U on the lower end, but U is a positive quantity, so that is the lower one. So so pay some attention to how the plus and minus signs work on this to keep things straight. If it comes from a scale family, remember we said that a scale family has densities, at least in the case of a continuous random variable, that have the value X over beta in the argument under the density, and then has a prefactor of 1 over beta that comes from transforming those random variables. So I'm going to take Q of X and beta to be the sum divided by beta. I'm going to write the sum as the statistic T of X, and that's a pivot for a continuous random variable that comes from a scale family. So now I'm going to choose L and U, so that the same thing is true. That's the beginning part. P sub beta of those data X such that L is less than or equal to Q of X sub beta is less than or equal to U. And again, we know that that object, that probability, does not depend upon the value beta. That is the magic of picking a pivotal quantity. In the case that I pick the sum T of X over beta as my pivot, then I'm left with that inequality, L less than or equal to the sum divided by beta less than or equal to U. And again, that doesn't depend upon beta. Now the goal of this little inversion exercise is to isolate beta. So we'll do that in a couple steps. So the first thing I'll do is I'll take inverses. So the L becomes 1 over L, the T of X over beta becomes beta over T of X, and then the U becomes 1 over U. And then when you take reciprocals, that reverses the direction of the inequalities. And now I'm going to multiply through by the statistic T of X. So T of X over L is greater than or equal to beta is greater than or equal to T of X over U. So now beta is trapped between two values. And I want to arrange it so that those two values have the desired probability gamma. Okay, so let's see how that works. If I have an exponential random variable, then if I look at the sum of those exponential random variables and I divide it by the parameter, then that is a gamma random variable with scale parameter 1. And it's a pivot. Okay, so if you want an equal tailed 95% confidence interval, and a little while from now, I'm going to give you unequal tailed 95% or different confidence interval that may have not equal tails, but we'll start off with equal ones. Then I'll put in the level of the, I did it with R, I'll put in the level of, that I want for the confidence level, gamma, and then I put in the tails that are going to be equal size. So 1 minus gamma in this case is 0.05, and I divide that by 2, and it's 0.025, but you could have put anything in there and use that to find alpha would be the symmetric, the probabilities of the symmetric tails. And then I ask myself what values for a gamma random variable with 10 degrees of freedom, or with shape parameter 10, the scale parameter is 1, so I'm not required to put it in there, gives me the alpha probability, which is the 0.025 probability in the case of gamma is 0.95, and 1 minus that, which is the 0.975 probability in this case. And so I asked what quantiles give me that, and the answer is 4.795 for the 2.5% quantile and 17.085 for the 97.5% quantile. And I'm going to use that to build a confidence interval. So I drew a density for the gamma random variable with shape parameter 10 here for you. And then I marked the values 4.795 and 17.085 as little teal-colored vertical lines that match the graph. And so the area between 4.795 and 17.085 is 95%. You'll notice, and maybe this is a little bit of a harbinger of things to come, the density on the left is bigger than the density on the right. And so if I move the vertical bar at 4.8 a little bit, then I get above 95% on a wider interval, but I get to move in the right-hand endpoint a little more because the density is lower. So I can play games to try to make a narrower confidence interval by appropriately thinking about ways to set that up. And we'll do that towards the end of the lecture. Okay, so but going back to the previous confidence interval that I'm trying to do on the beta parameter for the exponential, then we have said this gamma distribution with shape parameter 10 has a 95% probability of landing between 4.795 and 17.085. So I write that down. That's what we did our work to do. Then again, I can use the inversion. I skipped a couple of steps that I did in the previous one that says that if I want a 95% confidence interval for the beta parameter, then I just take my statistic, which is the sum of the 10 observations, divided by 4.795, and that's the upper end of my confidence interval. That's the beta hat sub L, and then, or beta hat sub U, excuse me, it's the upper end. And then I take that same sum of observations from the exponential random variable and divide it by a bigger number, 17.085. That becomes my beta hat of L, the lower end of the confidence interval. And I know have a 95% probability of being in that range. Okay, let's do it now for uniform random variables. This is also a scale family. And we have a tendency when we build these confidence intervals to pick a sufficient statistic. And so we know for the uniform random variables, the maximum of these random variables is a sufficient statistic for the parameter theta. So I'll use that. My T of X is just the maximum. And you can see that it's also a pivot. That is, the distribution of the maximum divided by theta is the same as the distribution. So that means I could take each of those random variables X divided by theta, and that would give me uniform random variables on the interval 0, 1. And so the distribution of the maximum divided by theta is independent of the parameter theta, and I can use it as a pivot. So we've already seen in the past what the distribution of n random variables that are uniformly distributed, and that distribution has the distribution function t to the n in the interval 0 to 1. So now I'm going to take advantage of that to build an equal-tailed gamma confidence interval. Okay, so I want my upper limit to match a probability that has, well, that's going to be 1 plus gamma over 2. So for example, if gamma is 0.95, then 1 plus 0.95 is 1.95 over 2 is 0.975. That'll be my upper limit. The lower limit will be 1 minus gamma over 2. So if gamma is 0.95, 1 minus 0.95 is 0.05, and 0.05 divided by 2 is 0.025. And you can check if I take 1 plus gamma over 2 and I subtract 1 minus gamma over 2, I get just gamma, right? The ones cancel and the two pieces of gamma add, and I get 2 gamma over 2. That's gamma. So that will give me an equal-tailed gamma confidence interval. So I just set a u to the n to be 1 plus gamma over 2, and I take the nth root of that. And then I set L to the n to be 1 minus gamma over 2, and I take the nth root of that, and that gives me my upper limit, my value u's and l's for my confidence interval for theta. So I know that that gamma will be the probability given that should be given to theta that my data land in there is. I'm going to multiply. I'm going to take the maximum, and I'm going to 1 minus gamma over 2 is a little bit less than 1, and so I take it to the power negative 1 over gamma, so that makes it bigger, greater than theta, and then t of x. That's 1 plus gamma over 2, so that's a little bit. Oh, it's a little bit bigger than the 1 minus gamma, so it's a smaller number, and I take it to the power negative 1 over n, and so I get a confidence interval now for the maximum value I can get in these uniform distributions by using the maximum of my observations divided by theta as a pivot, and using the maximum as the random variable for which I have a good understanding of the distribution function. Okay, now I'm going to just be much more abstract and inclusive in how we build probability transform, or build confidence intervals. I'm going to use the probability transform, which we saw last semester. What it tells you is that if I have, let's say, a random variable x, and its cumulative distribution function is f, and I have one that is a continuous random variable, then if I apply the cumulative distribution function to the random variable, that transforms the random variable to one that is uniform. And so I'm going to take advantage of the fact that f sub t of t, no matter what the value of theta is, will be a uniform random variable on the interval 0, 1. Okay, and now I'm not going to insist that my two tails be equal size, so the probability of the two tails is 1 minus gamma, right? Gamma is the probability that you're in the confidence interval, so the probability you're outside that confidence interval is 1 minus gamma. And I'm going to divide that into two pieces, alpha 1 and alpha 2, which may be equal, but not necessarily. So I'm going to look at the situation where f of t and theta is a decreasing function of theta. I'll say in a minute, it's easy to modify this argument if f is an increasing function of theta. The example that I'm going to do in a few minutes is one in which the cumulative distribution function is a decreasing function of theta for every value of t. So I'm going to use exactly this version of the theorem. So I'm going to define the upper limit for my confidence interval, two statistics, the upper limit of the confidence interval and the lower limit of the confidence interval, by solving an equation. So fix t and fix alpha 1. Then I want to find that value for which, that value of theta, so that if I plug in that as the parameter, I get alpha 1. And then correspondingly, I'm going to again fix t, and I'm going to take the probability 1 minus alpha 2, and I want to solve for that value of theta hat L that matches the probability 1 minus alpha 2. So that's the goal, and we'll see in a minute why that all works. I set things up correctly. Okay, and when that's done, then we have a random interval, theta hat sub L of t and theta hat sub u of t, and that random interval will be the confidence interval. And it will have, there would probability gamma of landing inside that confidence interval, irrespective of the parameter theta. So it's a gamma level confidence interval. So that's the theorem. And now when we go through the proof, you'll see exactly why we set up things the way we did. Okay, so I'm looking at the case that for the cumulative distribution function, if you fix t and you let theta vary, it's going to decrease as a function of theta. So as theta gets larger, then the cumulative distribution function value for that value of t drops. Okay, and 1 minus alpha 2, which is the, I can't remember, that's the upper tail, is got to be bigger than the value for the lower tail. Okay, and so since things are decreasing, that means the solution, so since 1 minus alpha 2 goes with, the solution of that goes with the parameter theta L, and alpha 1, the solution of that goes with the parameter theta U, and since the function f is decreasing as a function of theta, then picking larger values for the targets means that I had to pick smaller values to reach those target values. So if I look at ft theta L over t, that has to be a larger value than f sub t of theta hat u of t because my function is decreasing. Okay, so that gives me the flip in those inequalities. And on the other hand, if f of t of theta is less than alpha 1, then since things are decreasing as a function of theta, that means that the upper limit had to be less than theta, right? On the other hand, if I pick the other one, if f of t is greater than 1 minus alpha 2 because I have a decreasing function, because f is a decreasing function of theta, then theta hat L must be bigger than the theta I put in there, right? Because if I pick a larger value for 1 minus alpha of theta naught, that larger value, if I pick a larger value than 1 minus alpha 2, the object that solves for that larger value must be smaller than theta hat L, the one that solved it for exactly 1 minus alpha 2. So you may have to think through that a couple of times so you keep all those things straight. But if you put all that together, it tells you that f sub t of t and theta, which is a uniform distribution, landing between alpha 1 and 1 minus alpha 2, is exactly the same as all this work that I did, that theta L of t is less than or equal to theta is less or equal to theta u of t. Now, because I know that f sub t of t has a uniform distribution, then all I need to do to get the probability of f of t landing in that interval is just subtract the upper limit from the lower limit. But I arranged things so that subtracting the upper limit from the lower limit gave me gamma exactly. So that's why I know it's a gamma level confidence interval. Okay, now if f of t and theta is an increasing function of theta, then you'll have to, again, change those inequalities around. So for example, at the top, 1 minus alpha 2 greater than alpha 1 would imply, in this particular case, that theta L of t is greater than theta u of t, and away you go. And the other thing is, if you had a one-sided confidence interval, then you only have to worry about working with the probability gamma or 1 minus gamma, depending upon whether you're looking at an upper, a one-sided confidence interval where you're looking at an upper confidence level or a lower confidence interval. But it is simpler. You only have to think about one quantity rather than two. Okay, so I'm going to use this in the case where u is now uniform on minus theta to theta. And we know that the highest order statistic x sub superscript m and the lower order statistic x sub superscript 1, that pair of those statistics together form a minimal sufficient statistic for this case. You need two of them to do it. So So I'll take the difference between those two and I'll use that to determine the confidence interval. And I'll get to recall some things from last semester to tell you why that's such a good idea. Okay, so if x is a uniform random variable on minus theta to theta, then I could add the quantity theta to all those x's, and that'll shift the value of x's up by an amount theta, which means now xi plus theta are independent uniform random variables, but on the interval from 0 to 2 theta. Okay, so now I'm going to divide that by 2 theta, and that tells me that u sub I is a uniform random variable on the interval from 0 to 1. Okay, so now those u's are independent random variables on 0, 1. And I'm going to let tx be the top order statistic minus the bottom order statistic. So let's just do the substitution. So x sub n, well, the top order statistic for x will be corresponding to the top order statistic for u. And you get the top order statistic for x by taking u sub I times 2 theta, and it'll give you equation 2 ui equals xi plus theta, and then you bring a theta to the other side, so you get that the xi's are 2 theta ui minus theta. So I'll plug in the top order statistic, and I'll get un minus theta, and I'll plug in the bottom order statistic, I get u1 minus theta, and I multiply through by 2 theta because that's the change of scale. Then I simplify that expression inside the parentheses, and the thetas go away, right? It's minus theta minus negative theta, so those cancel to give 0. And I'm left with the top order statistic minus the bottom order statistic times 2 theta. Okay, and I'm going to call that object u sub superscript parentheses n minus u sub superscript parentheses 1 d. I'll just call it d to give it a name. But we'll know that name. So the distribution ft of theta is the probability that theta is less than or equal to t. That's equal to the probability that 2 theta d is less than or equal to t. That's the probability that d is less than or equal to t divided by 2 theta, and that is the distribution of d, which I don't know what it is yet, but it's evaluated at 2 divided by 2 theta. And the reason for going through this line of equalities is to show you that on the last line is I increase theta, t minus 2 theta decreases. Okay, and so that tells me that I have a set of conditional, a set of statistics f of t given theta that decreases in theta. So that means my theorem applies. So that's what all that was for, to show that the theorem applies. I have a decreasing function of theta, and I can solve those equations, which I gave you a minute ago. So it's, which is decreasing as a function of theta. Okay. Now, what is the distribution of the top order statistic minus the bottom order statistic if you have uniform distributions on the interval 0, 1? So we studied this last semester, and so I'll spend maybe a couple minutes to refresh this for you. If you look at n order statistics on the unit interval, then you think of the unit line. There are now n points on that unit interval, which are each of the values of the statistics, and the one that's on the left is the smallest order statistic, and the one that's on the right is the largest order statistic. If you recall that those n dots on the interval from 0 to 1 gives you n plus 1 spaces, right? Before you get to the first one, between the first and the second, between the second and third, and so on, and then between the nth one and the nth plus first one. Those gaps satisfy a Dirichlet random variable, and the Dirichlet random variable for each of those things has parameters. You may recall the parameters 1, 1, 1, 1, 1, 1. So they have the same distribution for each of these. Each of these gaps have the same distribution, no matter which gap you pick, of length 1. And so, but they're not independent because we know their sum is 1. They are exchangeable if all the parameters are the same. That is, if I swap the difference between the third and the fourth order statistic and the difference between the 7th and 8th order statistics, if I swap those two intervals, they still add up to 1 and the distributions don't change. So the other thing that we learned is that if you take the Dirichlet random variable with n parameters and you collapse it down, you get another Dirichlet random variable, but the parameters are not ones anymore. The parameters add in the Dirichlet random variable. So in this particular case, I'm going to collapse, I'm going to have un minus u1. So that is going to exclude the item at the top and the item at the bottom. If I bring those two together, then that's going to be one piece of what goes on. And then I can bring the other n minus 1 in the middle together so that I have just two groups, the group that is all the gaps between the first one, the nth one, and then the two on the outside. And when you get a Dirichlet random variable from n down to 2, that's a beta random variable. And the parameters are n minus 1 and 2. They're n minus 1 again because there are n minus 1 gaps involved in the order statistics from un minus u1, and there's the two gaps at the end, the left-hand endpoint and the right-hand endpoint. So that's how you get that beta distribution. That's sort of a long-winded answer. If you go back to the lectures on how we went from the order statistics to the Dirichlet distribution and review those, you'll see all that information in there. But the point is, I know the distribution of D exactly, and so I can use that to build confidence intervals. So I'll let Q sub D be the quantile function for D. Then Q sub D of alpha 1 is less or equal to T of X over 2 theta is less or equal to Q sub D of 1 minus alpha 2. Right? So I know the probability of that object in the middle is going to be gamma, right? Just by the way I set up quantiles. And so then I can invert it. I'll take the reciprocals again, and those reciprocals will change the order of the inequalities, and it just puts the numerators into the denominator and the denominators in the numerator. So it's, for example, now 1 divided by the alpha 1 quantile of D greater than or equal to 2 theta divided by my test statistic, which is the maximum minus the minimum, which is greater than 1 over the 1 minus alpha 2 quantile for D. And then I'll isolate theta by multiplying through by T of X and dividing through by 2, and that gives me a confidence interval, and I'm guaranteed that will be a 95% confidence interval, by the way I set things up. Okay, so let's look at this in a particular case. I'm going to let n be 16 and gamma be 0.95. And again, I'm going to look at a confidence interval with equal probability tails. So gamma is 0.95, and alpha is just the amount on the tails, which is 2.5%. So it's 1.1 minus 0.95 over 2. And then I just ask for what beta values give me the alpha quantile and the 1 minus alpha quantile. If I have, now remember it's beta n minus 1 comma 2, so if n is 16, I need 15 and 2. And it gives me the answers. The answers are 0.697 is the 2.5% quantile, and 0.984 is the 98.5% quantile. And there's a graph. You can see a lot of the stuff is piled around 0.9. I guess we know that the mode is around it's proportional to n minus 1 over 2. I think it's n minus 1 over 2n. We'll have to check on that. Okay, so now I've built the 95% confidence interval for these uniform distributions on minus theta to theta with equal tails. What if you don't like equal tails? What if you want to do something else? So as we've seen in the past, the only constraint that we have is that the sum of the tail probabilities equals 1 minus gamma. So that's just 5% in this case. So what if you decided that you don't want just any confidence interval, but you want the one with the shortest expected length? So that leads to an optimization problem, a constraint optimization problem. And a lot of questions in modern statistics boil down to an optimization problem. So it says, I want the expected value of the top of my confidence interval by the minus the bottom of my confidence interval be as small as possible. But I have a constraint. The constraint is the probability between the two has to be at least gamma, right? So it can be a confidence interval. So that of size gamma. So that would be the game you would play to try to find the confidence interval with the shortest expected length. I'm going to do a case that is somewhat easier just to see how it works, and it'll work in the cases that we have now. If the density is unimodal, then the first question I'm going to ask myself is, how do I maximize the probability over an interval of length c? So think of the cumulative distribution function evaluated at c and the cumulative distribution function evaluated at, at a value a and then a value a plus c. Okay, if that, and I want to, so I'm going to have a sliding window of length c, and I want to pick in that sliding window of length c the place where the probability is the largest. So I'm going to differentiate. So I look at the cumulative distribution function at the value a plus c. I'm going to divide it by the cumulative distribution function at the value a. I'm subtract from it the cumulative distribution function at the value of a. So that's probably, it lands between a and a plus c. I'll differentiate it with respect to a and see where I get. So if I do that, well, the derivative of the cumulative distribution function is just the density function. And so I am asking that the density function at a plus c and the density function a subtract to give 0. In other words, they're equal. So if you want to have the shortest, the confidence interval with the shortest expected length, and your situation where the density of the random variable you're looking at to build your confidence interval is unimodal, then a necessary criterion is that the density of the endpoints be 0. Now, is that minimizing it or maximizing it? I'm going to maximize the probability here to minimize the length of the interval. And so if the mode is T sub m, m for mode for the density, then in order for those two density functions to be equal, they can't be both on the same side of the mode. It's unimodal, so the densities would be different at a and a plus c. So they have to be on different sides of the mode in order for them to have the same density. So the mode is in the middle. Now, since it's unimodal, a is going to be less than the mode, and so the density function increases till you get to the mode, and so f prime of a has to be positive. On the other hand, a plus c is greater than the mode, so at that point the derivative is 0. So the derivative of a plus c is negative, the derivative of a is positive. So so if you took the second derivative of that, you would get something negative, and that means that you have a maximum. So that includes the maximum amount of probability that you could have. Just look for the place where the two densities are equal, and if it's unimodal, then you found the interval that has the highest probability for an interval of that length. Okay, so that shows that the probability is maximized. So what does this tell you? It tells you that if you have a distribution like the t distribution or the normal distribution that's symmetric about its mode, then we know that equal tail probabilities are the shortest. So all this work is not worth the effort if you have a symmetric function for which you build the confidence interval. So we want to look at those cases where we have asymmetric functions, but we saw a couple of them. We saw the beta distribution that was used to calculate confidence intervals for uniform random variables, and we saw gamma distributions for those situations where we're looking at confidence intervals for exponential random variables, and they're quite skewed. So I'm going to go back to the confidence interval, confidence interval that I built for uniform distributions on the interval from minus theta to theta and see what this tells me to do. So we want to find the shortest interval for D that has probability gamma. Okay, and so here's how R does that for me. I set a value for gamma, and then I'm going to create a function, and that function is I'm going to pick two quantiles that differ by an amount gamma. So that is a function of A. So I'll pick the gamma plus 8th quantile, and I'll pick the 8th quantile, and I'll subtract them. Okay, and so so the probability that you're between those two numbers is gamma plus A minus A, which is gamma. And so that's the value that I want. And so I have a function that tests that, and then there is a function in R that's optimizing. What it wants to do is maximize a function, but we're minimizing the length of the interval. And so you have to put in the command maximum equals false. The default command for optimize is maximum equals true. And then you have to give it an interval. So I gave an interval up to 5% because I don't want anything outside of that. It could be the case that the endpoint was the best thing. Pardon me. So it says that that this difference achieves a minimum at 0.48. So that's pretty close to 0.5. And so it is putting almost all of the tail probability, pardon me, on the left-hand side. And it says that the width of my confidence interval is 0.262. So that's the narrowest confidence interval that I can get by having a 95% confidence interval, and it tells me where to put it. And so then what are the values? So I just look at the value at the top level, and it's at 0.996, and I look at the value at the bottom level, and it's 0.783. So it shifted the confidence interval to the right. We'll talk about that in just a second. And then the theorem that we proved, or a little calculation that we did a few minutes ago, says that the density at the lower and upper level should be the same. And so I just checked to see that was true, and it's pretty close to the same. So we're having sort of numerical issues there. And I got 0.843 for one of them and 0.846 for the other. So they're off by a little bit. So I'm guessing that's just numerical problems. So let's just summarize what we have. Our first confidence interval had equal tails, and its width was 0.2868. And the density at the left endpoint was lower than the density on the right. So that means that I can move the endpoint on the left in by some amount, and I have to move the density on the right where the interval on the right where the density is higher by much less to keep it at 95%. So this suggests that we can shorten the confidence interval by moving the interval to the right. So that's what it told me to do. And so you can see the original confidence interval is given by the teal colored vertical lines. One is above about 0.69, the other is above, I can't remember, about 0.96. The shortest confidence interval I can get for this question has a left-hand endpoint that's somewhat higher, like 0.73, and then the right-hand endpoint is nearly 1. And you can see by the height of those brown line segments that the density at those two places is pretty much the same. Okay, so that is my tour through confidence intervals today. So I have one more lecture that I want to do on confidence intervals, and I want to do 3 things in that lecture. So it'll be 3 short pieces. One is I'm going to move from confidence to prediction. So a confidence interval says what I want to have a high probability that that my parameter is in a range. What a prediction interval says is I want a high probability that the next observation that I see will be in that range. This is used pretty often in linear regression, so that's the example that I'll use. So you may have a prediction given a value of x. You'll have a predicted value of y, and you'll have a variance for that y, or variance for, let's say, the slope of that value. But if you want to look at a variance for the predicted value of that, but if you, I mean, for the sorry, for the value of the confidence interval for the value you get above that value of x. But if you're trying to predict the next observation, that's much less certain. So you get larger intervals for the prediction interval. So that's one thing I want to do, talk about prediction a little bit. The second thing I want to do is I want to talk about bootstrapping, and it's another way to build confidence intervals that is in some sense free for everything, and we'll show how that works. I'll compare building bootstrap confidence intervals, say, to confidence intervals that you get from the delta method. It sort of works well when you have nonlinear transformations or in general, or something that's much more complicated to figure out. So I'll tell you a little bit about how the bootstrap works. Then the third thing I want to do is look at the nature of what happens when you look at the corresponding object in Bayesian statistics. There it's called a credible interval. So there you have a prior distribution. You have a set of observations. That observation gives you a posterior distribution, and then you construct an interval that has width gamma based upon the posterior distribution. In the Bayesian world of statistics, they use the phrase credible interval rather than confidence interval to distinguish that the strategies for obtaining these intervals are fundamentally different. So that's all I have to say today, unless there's another question out there. Okay, you guys were pretty quiet today. I hope you have a great week. Okay.
Hey, I had a small question regarding the homework.
Okay, let's see, let me get the homework. Did you see the homework?
Not yet.
Oh, huh. Okay, let's try again. Now can you see the homework?
Yeah, I can see it now.
Okay, I wonder what happened, but okay.
All right, so I had a question regarding challenging problem 1.
Oh, what? Challenging problem 1. Okay.
Yeah, so just part B. So I just wanted to confirm with you for part B, do you want us to assess that using the data or in a more general sense?
Oh, part B, yeah, it's a more general, well, which of the two is larger? That's easy, right? You computed two numbers and you can tell me which is larger.
Yeah.
Okay, so we'll give it away. The first one is larger, right? That is, if you do the matched pairs, it's larger than if you do the two-sample test.
Yeah, it's just
and
like
the matched pair test. Okay, the numerators of those two are the same.
Yeah.
The denominators of those two are different.
Yeah.
So if the first one gave me a bigger t-statistic than the second one, then the first one must have had a bigger denominator than the second one, right? That's how you get a bigger t-statistic. Smaller denominator than the second one.
Yeah.
So why did it have a smaller denominator?
Yeah, so for that, you want us to do it more theoretically, right? So
yeah, I mean, there's a computation. That's an abstract computation. And then abstract computation will tell you that there's a piece of information that's in the matched pair statistic sort of hidden that's not in the two-sample t-statistic.
Okay, that makes sense. All right, thank you.
Sure.
And Joe, I have a question on number 2. I think you answered this earlier in the lecture.
Oh yeah.
But
we always use let's see here, for beta we always use whatever R uses.
Well, there's scale and there's rate.
Yeah, we always use the rate parameter.
Rate, okay.
We always use rate in this class, and I only picked that because that's what R uses.
Oh.
Yeah, so I want to be consistent with R, so you don't have to type in the rate parameter. So I didn't have to do it in. I got to fudge the whole thing in the example because I moved everything to R equals 1, but right, for it to be a scale function, right, I divided it by beta, and that means that I'm using it as a rate parameter.
Okay.
Okay.
Yeah.
Any other questions out there?
Thank you.
You're welcome. Okay, so we'll say goodbye, and I'll see you guys, at 2 o'clock in office hours, and then sometime after that.
Have a great day and be safe.